Okay, I'm going to write short note for you. Number one. What is number one? What? A constant. Number one. Number two. Or not just datum, geometric datum. Geometric datum is at the centroid. Rule number three. Analysis starts from Y max. Rule number four. Q cannot cross the what? Rule number five. Shear flow can flow in one direction only. These are the 5 rules that you have to comply, and we cannot what? We cannot break. Are we clear? Okay, we break any of this, good luck. Okay, will not be right. Right. Now let's go back to derive. Okay, so I just show you examples. Okay, no, so we are now going back to derive. I forgot, did I record? It's so funny. Eugene always forget. Did I? I did. Okay, right. So we are going back. We are going to derive our shear is equal to 3/2. I can't remember the function now. Vy over A. Three over two. And then we have 1 minus by y squared over c squared. Okay. So going back to this figure over here. Okay. Going back to this figure over here. We found out that our QZ, so to derive this, we need to apply, okay, we need to apply shear stress XY is equal to Vy over IZZ QZ over what? T. Okay. And we know that QZ is equal to 0.5 P bracket C squared minus by what? Y squared. This is where we stop at. Then the next thing we need to find, we know that IZZ is equal to width depth cube over 12. Okay. So if we look over here, the axis of interest is our ZZ axis. And over here, if that's the case, this is our width. This direction, this is our depth. Okay. So this will be equal to the width is equal to B. The depth is equal to 2C cubed over 12. Okay, 2C cubed over 12. So over here, we get 8BC cubed over 12. Our second moment of area is equal to 2 over 3 BC cubed. Okay. So now we can put everything into the formula. Shear XY as a function of Y. Okay, because Y over here, remember what I told you all guys earlier, Y over here is your variable. Okay, Y over there. Stick key. Oh, okay, stick key. Okay, no. Okay. So from here, we know that Vy, then we have Izz. Izz is 2 over 3 BC cube. And then our QZ, so QZ we can write as half B C squared minus Y squared. Okay. And then this over here. Now the thickness is equal to what? So if this is our Vy, then I'm going to draw in red. This is our what? This is our Q. So remember what I told you, the thickness is perpendicular to the what? Shear flow. So this is our T. So from here, we can multiply this by B. Okay. So next, we need to do some canceling. We get rid of this. We get rid of this. And then I'm going to say note that A, which is the cross-sectional area, will be equal to 2CB, right? Or 2BC. Okay. So what I'm going to do now is I'm going to introduce A into the term over here. Okay. So we have shear XY as a function of Y. So this is equal to Vy. So the top is still the same. Half C squared minus Y squared, close bracket. And then the whole thing divide. I'm going to do what you guys learned in Laplace transform. I'm going to separate the 2BC, right? Then I will have C squared over 3. Is it Laplace transform where you cook? You all learn Laplace already or not yet? Yeah, you cook the equation, the relationship below. So from here, this will be equal to what? Vy, right? Half C squared minus Y squared. And then 2BC, you have your A. And then you have your C squared over 3. Okay. So when we move things around, you have By over A. Then you have 3 over 2. Then over here you have C squared minus Y squared. And the bottom part you have your C squared. You put everything in. By over A. You have 3 over 2. You will have 1 minus by Y squared over C squared. Okay. So from here, we know that the tau max will be equal to what? 3 over 2 Vy over A. And this will occur when what? When Y squared or when Y is equal to what? 0. Okay, when Y is equal to 0. So from this expression over here, if you look at this expression over here, so this is shear XY as a function of Y. And as you can see, this expression over here, right, is a what? Is a second order polynomial equation. Okay, it's a second order polynomial equation. So we take this, we come down to here. Okay, so now if I'm going to sketch the cross section, the shear stress distribution, right? Okay, so this is our shear stress, and this is our Y. This is our C value. Over here will be our minus C value, right? So we know at point C and at minus C, we know these 2 points over here. This line over here, this line over here, these are known as our what? Our terminals. Okay. So what you get is you get a relationship looking like this. So this expression over here, this is your shear xy as a function of y, and this is equal to Vy over A, 3 over 2, 1 minus y squared over c squared. And over here, your tau max, this will be equal to Vy over A, 3 over 2. Okay. Now, this is only true. Okay, this is only true. So what is only true? Tau max will occur at the centroid only if the thickness is what? Constant. If the thickness is not constant, then no. Okay, I repeat again. If the thickness is not constant, then you're in trouble. Okay, and I'd like to show you an example of this. Okay, if I can find it. Wait, did I post it in the first place? Hold on. I don't think I posted it. Okay. What I'm going to do is I'm going to give you a bonus. Hold on, bear with me. And the bonus I can't remember now. We are going to do this question. This is last year's term test. Okay. And I don't repeat my term test. But it's going to be a good bonus. The question that's coming up for your term test is going to be very what? Similar. Okay. What I'm showing you down here, it's one of the, you don't take pictures. Okay, I love optimization. But with optimization questions, I know who really understands and who don't understand. Okay, but I'm going to show you how to do optimization. Looking at the question over there, that is our beam. Okay. Now this was the time where I was a bit tricky. You see A, B, and C is to follow your student number. I will not do that to you this time. Okay, I don't need to get lost. Okay. Now, so the first part of the question is what is the largest P that the shear stress is not to exceed what? A certain load or a certain stress. The next question is an optimization question where it asks, what is the wall thickness of the beam such that the maximum shear at the centroid and the region with the smallest wall thickness are equal? That is a what? Optimization what? Question. Are we clear? Part B is optimization. Part A is straightforward. Now, so what are the things that you have to be really aware of? Okay, so I'm just going to put some figures over here. So this over here, I'm going to call it 500. Come on, please work. 500. and over here is 700. Okay, the load over on top is equal to what? 20 kilonewton. Okay, so just do this as I'm sorry. I think you all do need take a picture. I do apologize. Okay, can those of you just take a picture because you don't have the question. So what you see on this cross section, right? So if we draw our transformation, this is our what? This is our X, this is our Y, this is a rotation about Z. And if we look at the cross section, this is going to be our Y and this is going to be our Z. Okay. The first thing we ask yourself is the formula that we are going to apply is equal to shear stress. Oh, that's not 200. I do apologize. That's still P. My bad. Okay. The shear stress is equal to Vy over Izz Qz divided by T. Okay. So the first thing, in order to determine P, we need to locate the position of our max.